Lecture here. We're continuing on in the electrochemistry chapter there, which I think is 17. So last time we started talking about electrochemistry, really, the redox sort of reactions. A reminder: there are several definitions of redox of oxidation and reduction. Two of which we really sort of focus on here in this class. A couple of which are a little bit more suited for organic chemistry, but in general, when we talk about oxidation, it typically means that something has lost electrons. Something is going through reduction. We typically think about it in terms of a gain in electrons. And remember, you could use something like the oil rig or Leo Blanco's GER. When things do get oxidized or reduced, right? When they get oxidized, they become more positive because they lost electrons. Guys get reduced, become more negative. And we talked about sort of an easy way you can sort of figure out what is happening there, just kind of a basic sort of number line. And if you see yourself sort of moving in this direction, becoming more positive, that guy is going through oxidation. If you kind of see yourself moving in this direction, becoming more negative, it is going through reduction. So you could kind of simply move the oxidation numbers whichever way, and you could kind of determine what's being oxidized, what's being reduced. A couple of other definitions, which again we don't get too much into in sort of general chemistry, but it does mean, for example, that you gain some oxygen as you go from reactants to products is another sort of definition of oxidation, or you lose hydrogen as you go from reactants to products. So those are sort of three definitions of oxidation. And again, we usually in sort of general chemistry focus in on that guy. Opposite ones over here for reduction, it would be that you lost some oxygen as you go from reactants to products. You also would gain some hydrogen as you go from reactants to products. So again, the electron sort of definition is the one we sort of look at. That's not to be confused with, again, another important aspect of this, which is what is sometimes referred to, again, as the oxidizing agent or the reducing agent. And remember that the oxidizing agent is pretty much the substance that gets reduced, while the reducing agent is actually the substance that gets oxidized. And those guys could always usually be found on the reactant side of the reaction there. And the reason, again, they're sort of called those things sort of the opposites of their names. The oxidizing agent is the guy that gets reduced, and the reducing agent, the guy that gets oxidized. It's because they pretty much will cause that effect in the other sort of substance. So the oxidizing agent is the guy that gets reduced, which means he needs to gain electrons. In order for him to gain electrons, something else needs to lose electrons. So he causes the loss of electrons in another substance, thus causing it to be oxidized, and he's known as the oxidizing agent, and vice versa. The reducing agent is the one that gets oxidized. So as it gets oxidized, it's losing electrons. When it loses electrons, that's going to cause somebody else to gain those electrons and become reduced. And that's why, again, it's referred to as a reducing agent. So, sometimes people get those confused. Easy way to remember it is, I guess, if you're thinking about the agent, it is opposite of the name, basically, is the way you can identify those things. I think we finished up last time sort of in addition to obviously talking about basic redox reactions. And when basic redox reactions, we do have half reactions where, not like that, where, for example, we have somebody that loses electrons and maybe somebody that gains some electrons here. And these are, again, what I refer to as half reactions. This guy over here would be considered the oxidation half reaction. Again, because electrons are on the product side, this guy here would be our reduction half reaction, like it's being gained. And again, We know that because the electrons are on the reactant side. Remember, when we have half reactions, we can get the overall reaction by adding them together. Remember, though, that when we add them together, the one thing that we want to make sure of is the electrons are the same in both half reactions. So in this particular case, they are not. So we would have to kind of multiply 2 to everybody that's in here to get us to the same electrons, because the electrons should always, again, sort of cancel out when you do that, and you get, you know, something like this as our overall sort of reaction that is happening here. This particular made up example. Any questions on that there? So we also, again, like I was just saying, finished up talking about oxidation state, our number. And remember, this is sort of the charge that these elements would have in these sort of arrangements if all the electrons were really transferred. And they're not necessarily, as we talked about, for a lot of elements, and especially more so, I would say, probably your non-metals there. You know, a lot of times people have in their head sort of the charges we associate with the non-metals in sort of an ionic compound when they're hooked up with a metal. Like, for example, oxygen is -2, and sulfur is -2, and phosphorus is -3, and nitrogen is -3. Chlorine is -1, and so forth. Now, those will still be their oxidation numbers in a sort of ionic compound. So, you know, if you had iron 3 chloride, the chlorine would still be -1 in that situation because it's hooked up with a metal. In a situation where you have sort of those nonmetals with other nonmetals, you know, like say ClO minus, the chlorine may actually end up having a positive oxidation number in that arrangement. And really the main difference is in an ionic compound, we really are getting that true transfer of electrons. So, you know, pretty much the charge is with their oxidation numbers because we have the loss and the gaining of electrons. In sort of a covalent situation where we have sharing of electrons happening, we really don't have that full transfer of electrons, which means some of these elements will take up more of a perhaps positive charge or negative charge, depending on sort of their arrangement in that compound. So keep that in mind, and maybe not always the exact numbers that you may think about. Any questions on that there? Okay, so we are off to, I think we talked about oxidation numbers. So what we want to kind of talk about now is how to balance redox reactions in a little bit more complicated sort of situations, either acidic or basic sort of situations. And let's talk about, let's say if we were going to do this sort of reaction here, we're going to oxidize iron 2 to iron 3, and we're using dichromate here. And we would start with sort of a balanced equation here. And really the first thing that we would want to do is, you know, if it didn't tell us what's going on, we would want to try to figure out sort of what is being oxidized and what is being reduced. So we could look at, again, our oxidation numbers here, and we could definitely start assigning some oxidation numbers. The iron 2 is +2. We did this guy, I think, in the last example there, and we came up with a +6 there for the chromium. And that's because oxygen is -2, which is -14. There's 2 chromiums. Each one needs to be +6, so +12 and -14 gives us -2 overall. The iron over here is +3, and the chromium is +3 as well. So again, if you just kind of look at your number line, if you're not sure, if we look at the iron is starting at +2, which would be here. It's ending at +3, which would be moving in this direction. And that tells you it's going through oxidation. You don't even have to worry about the chromium, but you can still look at the chromium just in case you're not convinced. So chromium is +6, which would be over here. And it's ending at +3, which would be going in this direction. And it is going through reduction in this case. So we know that the oxidation, like it said, is the iron. That also means that this iron 2 here would be our reducing agent, right? Because it's going through oxidation. The chromium here would be our oxidizing agent in this case, as it is going through reduction. So the first thing you want to do if you're balancing sort of this equation in acidic conditions or even basic conditions, what you want to do is basically split everybody off into their half reactions. So when we split everybody off into their half reactions, we just want to kind of pick the two things that are related to each other. So iron on one side, iron on the other side. We have our dichromate, which is chromium on one side, and our chromium on the other side. Once you do that, what you want to do is essentially balance all the elements other than oxygen and hydrogen. So you want to kind of balance all the other elements besides carbon and hydrogen and oxygen. You kind of want to save hydrogen and oxygen for the end. What we do is, I think it's all in here. So just do that real quick. So again, splitting it off into its half reactions. Now what we want to do, like I mentioned, is sort of balance that elements other than really oxygen, hydrogen. So here we have 2 chromiums and 1 chromium. So to fix that, we would need to kind of put a 2 there to balance out the chromiums. And we would do that basically just like a regular reaction. We're just going to add our coefficient in front. Again, we're saving oxygen and hydrogen for a little bit later on here. So let's take a look at what we do with those. Once you've sort of balanced out your elements other than oxygen and hydrogen, now it's time to kind of focus in on oxygen. The way that we balance out oxygen is we actually add water to balance out oxygen. So whatever side needs the oxygen, we basically will add water to. So a couple of things about that. We add water to the side that needs the oxygen. But there is a situation here. Every time we add water, which is H2O, we're not only adding oxygen, but we're actually adding 2 hydrogens. So to make sure that we don't end up with the wrong number of hydrogens, we actually add 2 H pluses to the other side for every water we add. So water goes to one side. So originally here there were 7 oxygens, none on the right. We added the 7 waters to balance out the oxygens. Because we added 7 waters, that added 14 hydrogens to the right-hand side. To balance that out, we add 14 H pluses to the other side. Again, that's going to keep us balanced in terms of both hydrogen, obviously, as well as oxygen. Any questions on that move there? Speaking of hydrogen, there could be a situation where maybe you start out with an extra hydrogen on one side versus the other. In this situation as well, you could just add an H plus to the other side. So again, we kind of use H plus to balance out hydrogen. And if you kind of start out with one less hydrogen there, you want to kind of add it in to begin with. Otherwise, again, you'll be short hydrogens. Once we pretty much have balanced all the elements, balanced oxygen by adding water, added the appropriate amount of H pluses, now we're ready to balance out the overall charge on each side by adding electrons. So what we want to do is basically add electrons to balance out the overall charge. So how do we get the overall charge? Well, if we look in our first half reaction, which is iron, it is +2. Overall charge on the left. Overall charge on the right is +3. So on the right-hand side here, we need 1 electron, which gives us a -1. +3 and -1 is +2 on the right and +2 on the left. They are equal in terms of their charge. They do not have to equal 0 on both sides, but they do need to equal the exact same number. So +2 and +2 is good overall. We also kind of know we're okay because we added electrons to the right-hand side. And if you remember, this is our oxidation half reaction, which means those electrons should end up there on the right-hand side. So that's actually good. If we look over here, before we added the electrons, we basically got plus 14 happening for the hydrogens. Now, this entire thing, who cares about the individual sort of oxidation numbers? We know that they all add up to -2. So we just need to really look at the -2 there. That gives us a grand total of plus 12 happening on the left-hand side. On the right-hand side, that is plus 6, and that is 0, which means right-hand side plus 6 overall, left-hand side plus 12. That is why we added 6 electrons to the left-hand side. -6 and plus 12 gives you a plus 6 overall. We are balanced in terms of the charge on each side in there as well. In addition, we did add it to the reactant side, which tells us we know this is our reduction half reaction, which is where we would expect it to be added. Any questions on that there? Now that you have your electrons, we really want to add them back together. But one important thing that we talked about just a second ago is before we add it back together, the electrons in each half reaction do need to be the same. And we have a problem here because top of half reaction is 1 electron, bottom half reaction is 6 electrons. That means to the top half reaction, we need to multiply the entire thing by 6 in order for it to basically end up with the correct number of electrons. So that's what we would do. We're going to multiply again just the top reaction all the way across by 6. Purpose of that is so that we can balance out and cancel out the 6 electrons that are in the other half reaction. Once we do that, we're now ready to actually add everybody back together. And when we do that, we're going to add back together the entire half reaction, canceling out our electrons. And by the way, the electrons should always cancel out. They should always be on opposite sides like we talked about and always sort of completely cancel out. That leaves us this equation here. And this equation here would be it balanced in acidic conditions. So this would be an equation that's balanced in acidic conditions. How do I know it's balanced in acidic conditions? Well, I see H plus, so H plus is like an acid, so that's acidic conditions actually in this reaction. How do I know it's really balanced? Well, when we say it's balanced in this situation, it should be balanced really 2 ways. It should be balanced like a normal reaction, which means if I count up all the elements on each side, I should have the same amount. I have 14 hydrogens on the left, 14 on the right. I have 2 CRs on the left, 2 CRs on the right. I have 7 oxygens on the left, 7 on the right, and 6 irons on the left and 6 irons on the right. So like a normal equation, we have the same number of elements on each side. The second way, so you basically should have same number of elements on both sides. The other thing is you should have the same charge on both sides. Again, does not have to equal 0, but it does need to be the exact same overall charge. So if I do some adding here, I got a plus 14 happening for the H pluses. I have a plus 12. That's a lot of math there, but we're going to go with plus 26 when I add that together. And a minus 2 happening here for the dichromate. So that's a grand total of plus 24 happening on the left-hand side in terms of the overall charge. Overall charge here on the right-hand side, that's 6 times 3 is plus 18. Plus 6 more is plus 24 on the right-hand side. So this is balanced correctly both ways, number of elements and also the overall charge on each side. Any questions on that? Now, these are the steps that we would follow if we were going to balance this reaction in acidic conditions. What would we do if we were going to balance this reaction in basic conditions? So let's say we wanted to do basic conditions. There are a number of ways you could approach basic conditions, but I've found probably the easiest way is to actually just do everything like we just did in acidic conditions, and then at the end, turn it into basic conditions. So when we turn it into basic conditions, what we're going to do is basically add OH minus to both sides. And you may be wondering, how much OH minus should I add? It should be equal to the number of H pluses you have. So if we take our equation from above, and I'm just going to recopy it here, 14H pluses plus Cr2O7 2 minus plus 6 of these iron 2s gives us 6 of these guys, couple of those guys, and 7 of these guys. Now, again, I would get to this equation like we just talked about, basically just balance it in acidic conditions. At this point, what I would do is go, okay, I have 14 H pluses. That means I would add 14 OH minuses to both sides. Again, not just one side, but both sides there. Now, what will happen is you will have a side, like we see here, that has both H plus and OH minus on it. This side right here. When you have H plus and OH minus near each other, there's a very strong attraction, and those guys want to come together and form water. So they will come together and actually form water in this situation. And that would get us 14 waters from here, plus Cr2O7 2 minus, plus 6 of these guys, going to the other side of 6 iron 3s, plus 2 of these, and 7 of those, and 14 of those. Now you could also see that I have 7 waters on the right-hand side. I have 14 waters on the other side. You could reduce it down, thinking of the arrow as like an equal sign, subtracting basically the 7 waters to the other side. When you do that, that's going to leave you 7 waters plus dichromate plus iron 2, iron 3, and this. Now, if we did not mess anything up here, we should be balanced still in 2 ways by number of elements. So if we take a quick look, 14 hydrogen on the left, 14 on the right, 2 chromiums on the left, 2 on the right, 7 oxygens on the left, plus 7 more is 14, 14 on the right, 6 irons on the left, and 6 on the right. Overall charge on the left-hand side, 6 times plus 2 is plus 12, and a minus 2 there from here is a, what we got there, plus 12 and minus 2 is a plus 10. On the right-hand side here, we have plus 18, and 6 more is 24, minus 14 is also a plus 10. So this would be balanced in basic conditions here. Any questions on that? This is by far probably the easiest approach to balancing something in basic conditions, to just do it in acidic conditions and turn it into basic conditions. You could add your hydroxide way early on after you do your electrons or before you do your electrons and all that. But there's a lot more canceling out and stuff to do. So it's best to kind of wait to the end. By the way, you may be wondering again how I know this is balanced in basic conditions. Well, I don't see H plus in this reaction, but I see OH minus there, right? Which tells me basic conditions. Any questions on how to balance these equations here? All right, so let's see what we got. So why don't you take a few moments here, and why don't you give one a go here and see what you come up with. We'll start with the equation there. So there you go. So starting with this equation, let's balance this in basic conditions. So take some moments here and start working on it and see what you come up with. Okay, so I know you may not be finished, but let's take a look and kind of see how you're progressing. So this would be our unbalanced equation that was sort of given to us. We do want to maybe kind of think about what's happening here, but we can't split it off into two half reactions. You can just do that simply by, again, looking at what is related to each other. So obviously the I minus is related to the I2. Obviously the thing with the Mn on both sides are related to each other. 4 minus goes to MnO2. Just going to back that up so I have somewhere right. And if we look at sort of what's happening here in terms of oxidation numbers for each of these guys, we could look at the I minus, which is -1, and the I2 is an oxidation state of 0. So looking at that, we're starting at -1 and ending at 0, which means this guy is going through our oxidation. If we look at the Mn here, and the first guy, this guy, oxygen is going to be -2. That's -8, which means to balance it out, actually the Mn here is taking on a +7 oxidation number. -8 and +7 gives us a -1 overall charge. Looking at the other Mn on the other side, -2 gives us a -4, and that's a +4 would be a better math there probably. +4 balances out the -4, gives us 0. In terms of the Mn, starting at +7, ending at +4, which is heading in this direction, which is reduction. And now we know, again, this is our oxidation half reaction. This is our reduction half reaction. We also know in this particular case that the I minus is our reducing agent. And really the MnO4 minus, or really the Mn part of it, is our oxidizing agent. First off, any questions on those parts there? Okay, so I'm just going to erase some of these charges so they don't kind of get in the way here. There we go. Okay, so now that we have this, basically what we want to do, right, is at this point we want to balance everything other than oxygen and hydrogen. In this case, we do need to put a 2 there in front of the iodine because there's 2 on the right-hand side. In this case, the Mn on the left is 1 and there's 1 on the right, so we're okay with that one. The next thing that we want to do is add our water to balance out our oxygen. There's no oxygen in the top half reaction, so we don't have to worry about it. On the bottom half reaction, on the left, excuse me, on the left is 4 oxygens. On the right is 2 oxygens. That means in order to balance out the oxygens, we would need to add 2 waters to the right-hand side. By doing that, that gives us a grand total of 4 oxygens on the right and 4 oxygens on the left. Remember that when we add the water, we're also adding hydrogen, which means we then need to go to the opposite side so we're not unbalanced and add 4 H pluses. Those 4 H pluses again come from the water that was added to the other side. Any questions on that there? All right, now that we've balanced everything, we balanced oxygen, we balanced hydrogen and all that good stuff, what's left now is to balance out the overall charge on each side. Overall charge on the left-hand side of the top half reaction is -2, 2 times -1. Overall charge on the right-hand side is still 0, which means the right-hand side here will need 2 electrons. That gives us a -2 on the right, -2 on the left. Also makes sense. This is an oxidation half reaction. We see our electrons added to the correct side. Coming to the bottom, we have basically +4 here. Again, this entire thing really has a -1. So we could just look at the overall charge there. That gives us really a +3 situation happening over there. Right-hand side, there's no really oxidation number or charge on anybody here. So that's a grand total of 0. That means that the left-hand side here will need 3 electrons. 3 electrons, again, will balance out our overall charge, giving us -3 and -1 is -4, and +4 is 0 on the left and 0 on the right. Any questions on adding those electrons? Again, I'm just going to kind of erase this so it's not so cluttered. We're technically ready to add these guys back together at this point, but we do have sort of a situation here, and the situation is we do not have the same number of electrons in each half reaction. In this case, we're looking for 6. So we do need to multiply the top half reaction by 3. That will give us 6 electrons. We need to multiply the bottom half reaction by 2. That will also give us 6 electrons. So I'm going to do that and rewrite those equations. So that's going to give me 6i minus, going across the arrow there, 3i2 plus 6 electrons. I'm now going to distribute the 2 across the entire bottom reaction. That's going to give me 6 electrons plus 8 H pluses plus 2 of those. Gives me 2 of that plus 4 of that there. At this point, we can now add this back together, remembering what the goal is before we add them together, or when we're ready to add them together, is the electrons should cancel out completely, which they do. Again, anything on opposite sides of the arrow that are the same thing can either cancel out or reduce down. If we do that, we are now left with 8 H pluses on the left plus 6 iodides plus a couple of these guys. Going to the other side, 3 iodides plus a couple of those and 4 of those. Technically speaking, what we are looking at here would be this reaction balanced in acidic conditions. Again, we see the H plus there on the left-hand side telling us it is balanced in acidic conditions. Just to verify we didn't screw up anywhere, which is sometimes a good idea. Quickly looking, we see 8 hydrogens on the left, 8 on the right, 6 iodines on the left, 6 on the right, 2 MNs and 2 MNs, and a grand total of looks like 8 oxygens on the left, and 4 oxygens is 8. Overall charge at this point on the left-hand side is +8, -6, and -2, which is 0 and 0. So again, it is balanced here in acidic conditions. Any questions on that so far? Remember, we're not really going for acidic conditions here in this particular one. We are going for basic conditions. So again, this is the procedure you should follow for basic conditions as well. At this point, this is where we're going to add OH minus to both sides equal to the amount of H pluses. So in this case, that means we're going to add 8 OH minuses to the left and 8 OH minuses to the right. These two guys here will combine and make 8 waters, plus everything else here will remain the same. And what usually happens in this situation is what we see here. We usually have some waters that can then be reduced. So 4 waters on the right will reduce this guy down to 4 waters on the left, leaving everything else here the same, except for obviously the water's gone on the right-hand side. And if you copy it right, that also helps. There we go. And at this point, this should be it, balanced in basic conditions at this point. Again, we could do a quick run through to make sure. 8 hydrogen on the left, 8 on the right. We got 8 and 4 oxygens. That's 12 oxygens. 8 and 4 oxygens on the right, 12. 6 iodines, 2 MNs on both sides. Overall charge on the left-hand side is now -8. Overall charge on the right-hand side -8. So we are balanced in both ways. Again, we know it's actually basic because when we look at the final reaction, I see OH minus, which tells me it's basic. Any questions on any of those steps there? Okay, why don't we just look at maybe one more here. Actually, we'll skip that one. Why don't we do this one here? So why don't you balance this one in acidic conditions again, just to make sure everybody hopefully on the same page in terms of this stuff. Okay, so let's take a look here and see. So really want to just kind of start off all these pretty much the same way. You just want to kind of break it off into their half reactions. Simplest way to do that is just find the same elements on each side. So obviously this guy's got some chromium in there, which is our dichromate. We got some Cr3 plus happening. We also have some carbon, which is in our oxalate here, and our carbon dioxide happening there. Also, probably a good idea is, again, sort of maybe figure out, what is being oxidized, what is being reduced if you're not sure. Again, if we kind of look at our number line here, we've already done this guy a number of times, and we know that the chromium in this case is +6. The chromium over here is obviously +3. So in terms of the chromium, again, we're going from +6 heading in the direction of +3, which would be going in that direction. And that is reduction when we're kind of becoming more negative. Now, excuse me, let's go the wrong way. So looking over here at our oxygen, which is -2, get that right, it's -8. So it should be -2 overall. So we really need this to be like a +6 happening. So that's like a +3 happening there with our carbon. On the other side, we have -2. And we also have +4 in that case. So what we see here with the carbon is starting at +3, heading to +4, moving in that direction, which is oxidation. And by the way, once we obviously determined that this was reduction, by default, this guy had to be oxidation. In addition, what that means is we could also identify our oxidizing agents or reducing agents. So in this particular case, because the dichromate is going through reduction, the dichromate here would be our oxidizing agent. The oxalate here is going through oxidation. It would be our reducing agent. Any questions on sort of how to identify all those things there? All right, now that we got it sort of all identified and all that good stuff, we're really in the process now of moving to balancing. We want to balance everything besides oxygen and hydrogen. So in this case, we do need a 2 there for the chromium. In addition, we actually do need a 2 there for the carbon. There's 2 on the left and only 1 on the right. So we do need to put a 2 in front of it there. At this point, we're going to balance our oxygen. Top guy has 7 oxygens on the left, none on the right, which means top guy should end up with 7 waters. When we add the 7 waters, that's going to allow us now to have to add 14 H pluses to the other side just to make sure everything's balanced. When we go to the bottom, we have 4 oxygens on the left, and actually by putting the coefficient here, we actually now have 4 oxygens on the right. So the bottom one actually in this case will not need any waters added. It actually self-corrected, if you will, by adding that coefficient in that case. Any questions on that there? At this point, we're now ready to balance a charge. So overall charge happening here is we got +14 from this guy. We have a -2 from this guy. That is an overall +12 charge happening on the left. Right hand side, we have a +6 happening and a 0 happening, which means overall charge on the right is +6. That means that the left hand side here will need 6 electrons. to do that. 6 electrons and plus 12 gives me a plus 6 now over on the left to match the plus 6 that's over there. So now with this, minus 6 gives us now a new plus 6 over here. Any questions on that there? Coming over here, overall charge on the left-hand side is actually minus 2. Overall charge here is 0, meaning that the electrons will need to go over here on the right-hand side, giving us minus 2 and minus 2. Again, balanced on both sides. These addition of the electrons are on opposite sides of the arrow, which is good. And they also agree with what we know. This is on the left-hand side, and that's what it should be for a reduction. And over here, our oxidation is on the right-hand side or the product side, and that agrees with an oxidation. So again, where we added the electrons does make sense based on what we sort of determined earlier. Any questions up to that point? All right, well, we're ready to add these together, but we can't do that just yet because the top half reaction has 6 electrons, bottom half reaction has only 2. In this case, we just need to multiply really the bottom half reaction by 3 to get us to 6. What I'm going to do is just kind of recopy both reactions down on the bottom here. So we had 6 electrons plus 14 of those guys, plus a couple of those guys, giving us this plus this. Multiplying that 3 all the way across gives us this. And it gives us that there and this there. And that's good because now we're good to go to add together. Electrons should always completely cancel out. In this case, it looks like nothing else will cancel. So everything on the left-hand side of the arrow stays there. Everybody on the right-hand side stays there. So just recopying what we got going on in this case. Copying it correctly would also help, I suppose. And again, if we did not mess anything up at this point, we should be balanced now in acidic conditions. Again, we see in our equation the H plus, which kind of tells us it's acidic. And we know we kind of did something right there, didn't mess up something, hopefully. But more importantly, we do want to just quickly double check. And again, if we look on the left-hand side there, we have 14 hydrogens, right-hand side, 14 hydrogens, left-hand side, 2 CRs, right-hand side, 2 CRs, left-hand side looks like 12 and 7 is a lot, 19 oxygens. Other side, same deal, 12 and 7 gives us 19 oxygens and 6 carbons on each side. So we're balanced again in terms of the elements. Looking at the overall charge here again to make sure that we are balanced, this guy is going to yield us a plus 14. This guy will yield us a minus 2 for the overall charge, and this guy will yield us a minus 6. So adding all that together looks like it's a plus 6 overall. Coming to the right-hand side, this is going to yield us a plus 6. This is 0, and this is 0. So plus 6 and plus 6. Again, it is balanced both ways, both the overall charge on both sides and elements on each side. Any questions on that steps there? Okay, so again, like I kind of mentioned the other day, we're going over this, and depending on maybe who you had for first semester, maybe you did a lot of this, maybe you didn't do a lot of it. So hopefully this puts everybody kind of on the same page in terms of these redox reactions, how to balance them, because you will need to know how to balance obviously redox reactions and in certain situations as well, obviously in lab as well. You'll need to know how to balance them in acidic and basic conditions. Any questions on any of those steps? Okay. So what we're going to then talk about really is sort of applying these sort of redox reactions to what are referred to as galvanic cells. And a galvanic cell really is just a sort of redox reaction that is taking place. A traditional sort of galvanic cell that you could build in a laboratory is kind of like what we see here in the picture. There's several sort of parts to it, but let's take a look at it. So on the left-hand side in this picture, we have a solid electrode, in this case made up of zinc metal. It is sitting in a solution that has zinc ions in it, and that is typical way you kind of set up a galvanic cell. We have sort of a solid electrode. It sits in sort of a solution that contains the same ion that's floating around in it. And what's going to happen on this particular side, this is what is known as the anode compartment. And on the anode side, oxidation occurs. So in the anode part of a galvanic cell, that is where we see oxidation, which means it's going to lose electrons. So really, what does that mean? If we kind of look on the super zoom here, what's going to happen is those zinc guys that are on the solid electrode are going to give up electrons. And when they give up electrons, they will become positively charged and essentially go from the solid and then go for a swim, basically. Anything with a positive charge pretty much is an aqueous sort of solution. It's really floating around in the solution. So what we have are these zinc guys are sort of jumping off the solid, going into the solution and making these zinc plus. The electrons that they're losing will then travel through a wire, as you can see here. Oftentimes we do have a voltage meter hooked up there. As the electrons kind of go through, we get a certain number of voltage, kind of like a battery and stuff like that. Coming to the other side of our galvanic cell, where we also have usually a solid electrode that's hooked up. This particular electrode is made up of copper, and we see the similar situation as we see on the left-hand side. Usually this electrode, again, is in a solution that contains the same ion that's in the solid electrode. So in this case, we have copper 2 ions that are floating around in the solution. This side of the galvanic cell is what is known as the cathode. And this is where reduction takes place, or the gaining of electrons, which makes sense. Electrons are traveling from our anode to our cathode. They're going to come through the wire. They're going to kind of come down through into the solution, hook up with some of those copper 2 ions that are basically floating around. And what's going to happen is the reduction reaction is going to happen. We're going to go with the copper 2 plus a couple of electrons, making some solid copper. So kind of like the copper is going to come out of the solution in this particular case. And we're going to kind of plate copper onto the solid electrode, if you want to kind of think about it in that situation. There's sort of a potential difference or energy difference between our charge difference, I guess is the way to think about it, between the anode compartment and the cathode compartment. You could think of the cathode compartment as being a little bit more positive, going to bring those electrons towards that side and keep the flow going. Now, if we ran a galvanic cell like this and we did not have perhaps this guy connecting it, which is another very important part of a galvanic cell, this is what is known as a salt bridge. A salt bridge connects both sides of the galvanic cell. It is usually filled with some type of ionic compound, like we see in this example, potassium chloride. And we see the potassium ions will actually float down towards the cathode side. The chloride ions are going to float towards the anode side. There's also some plugs there, so the solution doesn't come out. It's just able to kind of slowly monitor and float one way or the other. It doesn't fully flow in there. Again, it just kind of slowly diffuses into there. Why do we need sort of this salt bridge here in this situation? What happens if we didn't have it in that situation? Well, if we didn't have in that situation, just find somewhere I can scribble. Whoops, I think that was a place I could scribble. Perfect. So if you think about what's sort of happening just in the beakers, right? In our anode and cathode sort of beakers, we are having this electrode that's sitting there, and basically it's going through reduction, which means it's dropping out into this solution a bunch of positive charge, right? And that's coming, for example, with the zinc, right? So as the zinc like drops in, for in the example we are just looking at, We're getting a bunch of these zinc ions, right? We have these electrons which are transferring to this side. And remember on this side, we had like copper 2, and we also had some other ion there like sulfate. And the electrons are coming in, and this guy is coming out. And what we're doing is getting rid of the positive charge over on this side, and we're building up a lot of negative charge, right? So if we ran the cell without the salt bridge, we're going to run into a little bit of a problem here. I'm going to try to connect my sides here, because we're having electrons going in this direction, right? From the anode to cathode. If we ran it without the salt bridge, we're going to end up getting a buildup of positive charge on the left-hand side and a buildup of negative charge on the right-hand side. And that's problematic because electrons are negative. They are definitely not going to want to head towards the negative side. They're going to go, no, thank you. We rather go this way, right? Because, hey, this guy's positive. And this cell will essentially sort of stop running. You won't get voltage and stuff like that because you got too much of a buildup of negative charge happening over here, buildup of positive charge happening here on this side. Remember, like I said earlier, the cathode usually has kind of a more positive sort of charge, which is going to bring those electrons to that side. We could correct this problem by inserting our salt bridge. When we insert our salt bridge, as we saw on the previous slide, they were using potassium chloride. So our potassium ion is going to go into here, right? When the potassium ion starts to go in there, what is that going to do? That is basically going to add some positive charge, which is going to keep that buildup of negative charge from happening and actually maybe even make it a little bit more positive now. What's going to happen when the chloride comes in here? Chloride comes in here, negative and positive. That's going to now take out a lot of that positive charge and maybe return the balance a little bit more to negative charge. And that's going to then make the electrons go, okay, that's much better. We will continue on down this road because it's more positive in that direction. So the salt bridge plays sort of a very important part in sort of keeping the charges correctly balanced to allow the galvanic cell to continue to function correctly. Again, without it, you really will get sort of that buildup of charge on each side, which is not really beneficial to allowing those electrons to continue to travel from the anode to the cathode. Questions on that? So ultimately what we have is, as you can see here, two half reactions. We have basically in this cell our oxidation half reaction, and we have our reduction half reaction here. And if we add them back together, we get really the net reaction that's occurring here, which is basically the zinc plus the copper 2 ions are going to the zinc 2 plus and the solid copper in this case. So again, zinc going through oxidation, copper going through reduction in this case. And again, that flow of electrons going from our anode to our cathode. Again, our cathode being a little bit more positively charged, helping kind of pull those electrons to the other side. What are electrons able to do? Again, we'll talk about in this chapter, but again, very much like a battery, you know, it essentially can do some type of work and stuff like that. Any questions on that there? So you definitely need to know the different parts, obviously, of a galvanic cell, what it looks like, how you would construct one here in a laboratory. So when we talk about galvanic cells, we do talk about a couple of things. And one thing is sort of what I just mentioned. There is what is sometimes referred to as sort of a potential difference between sort of the anode and cathode side. You can kind of think of that as sort of like a positive difference. Again, that's really what's going to kind of bring those electrons from one side to the next. Here is like that copper zinc cell hooked up. You could kind of see here we have our solid electrodes, we have our solutions. Again, this has got zinc ions floating around. This guy's got copper ions floating around. And again, we have that oxidation reduction. Hard to see here, but there actually is a salt bridge right there, kind of connecting the two tubes. Obviously, you hook it to some leads to a voltage meter, you get some positive voltage sort of happening. So when we talk about cell voltage, a voltage 1 joule of work per coulomb of energy. So a volt is a joule over a coulomb. That's a sort of a conversion that we'll use a little bit later on here. And it's sometimes referred to as electromotive force or EMF or cell potential. So in questions, if they ask you to calculate the cell voltage or the EMF or the cell potential, they're pretty much asking you to calculate the voltage. So those are typically, what they're asking you to calculate. If we look at our reaction, we can also display our reaction in a very common way, which is what is referred to as a cell diagram. And cell diagrams are pretty much arranged in a certain way. They're arranged from anode to cathode. So just to kind of look at this, this is sort of, if you will, on the left-hand side here, this is really your anode compartment here. So that's like your anode compartment. On the right-hand side is your cathode compartment. And how does these guys sort of relate to the equation, and how are they put in there? They're put in there basically by reactant, product, reactant, product. So if we look here, zinc solid, reactant, zinc with a +2 charge, product. Coming over here on the cathode part, copper with a +2 charge, reactant, copper with no charge, product. So that is sort of how they're sort of arranged. We go from reactant, we put a line between the reactant and product side of our anode reaction. These two lines right here represents the salt bridge. And coming over here to sort of our cathode compartment, we have our reactant, and we also have a line to separate it out from our product. You also see that sometimes concentrations are put in there. And sometimes people will list those in, and it's only for obviously the ones that are ions that are floating around in the solution. When we talk about concentrations, remember a couple of things about standard conditions. Remember, 1 molar for concentration is standard concentration. And if we're doing something with pressure, 1 atmosphere is standard pressure that's happening. And you can come across some pressure sort of values that occur here. And we'll see that here in just a second. Any questions on how to sort of write a cell diagram? Again, if we wanted to basically take our cell diagram and turn it into an equation or a reaction, we basically follow that pattern. So we would start here and go, okay, this zinc is the first thing listed. That is my reactant. Zinc on the second guy listed, that is my product. Copper, first guy listed on the cathode side, would be a reactant. And copper on the product side there would be a product, obviously, in this case. So again, that's how you can kind of go from cell diagram to equation. And you do need to be able to, again, kind of go both ways there. Take an equation and write a cell diagram, or have a cell diagram and write the equation from it. Any questions on that? Okay, so let's talk about sort of what we could do with some of these things. And for example, if we build up a galvanic cell here, this one is a little bit different than some of the ones that we've seen. First off, we have a zinc over here acting as our anode. Same sort of setup. Again, in the solution would be something like zinc sulfate. What that really is supplying is zinc ions floating around, also sulfate ions floating around. Over here, we actually have a different sort of electrode hooked up. This is on our cathode side. This is actually the hydrogen electrode. And in this case, we're actually using hydrogen gas as sort of the electrode, along with some hydrochloric acid going to supply H plus and Cl minus in that solution. You'll also notice that because hydrogen gas is a gas and there's not really a hydrogen sort of solid metal that you could use, we will sometimes use something like platinum, carbon, graphite, something like that to sort of act as the physical sort of electrode to allow the electrons to have a place to follow down in the wire and sort of come in and do its deal. In place of, obviously, there's no hydrogen solid sort of electrode or anything like that that you could use. So you'll sometimes see, again, some type of metal like that that's not going to be really reactive per se, like graphite, platinum, something like that, that's going to be used as sort of the physical application here. So if we look at this, this is our cell diagram, and because one of our electrodes involves a gas, we actually see a couple different things happening here. This is our anode. So again, this would be our reactant if we were going to write the overall equation. This would be our product, the second guy there, right? So again, reactant, product. This is our salt bridge, which means on the other side here, we have our H plus, which would be our reactant. And this guy here would be our product, H2 in this case, and probably need to do some balancing, so you can put a 2 there. And then we would have, obviously, our reaction. We also see a couple different things involved here. We see the pressure instead of the concentration because we're dealing with a gas. We also see the inclusion of the solid electrode, which again, not really part of the reaction or doing anything other than it is sort of the sort of physical part of that cell or the cathode side. So it sometimes is included in the cell diagram. But again, you can kind of see, you can get the overall reaction like I just did there by kind of going from our sort of cell diagram to our reaction. We do see our oxidation occurring here again, zinc going from 0 to +2, becoming more positive, going through oxidation, right? Heading in this direction on our number scale. Hydrogen here actually going from +1 to 0 in this case. So starting at +1, going towards 0, going through reduction is the hydrogen in this particular example. Any questions on that? So what is a standard reduction potential? A standard reduction potential, as its name implies, it is the voltage that's associated with the reduction reaction in electrodes when everybody's sort of under standard conditions, 1 molar or 1 atmosphere for pressure. SRP, standard reduction potential, is sometimes abbreviated as SRP values. So SRP standing for standard reduction potential values. And when we look at it, we need to figure out really what is everybody's value. So much like in chemistry, what they do is they actually assign something as sort of a standard, and they give that guy sort of the standard value, and they compare everybody else to it. So what they chose for standard reduction potentials is the hydrogen electrode, and they call it the standard hydrogen electrode, which is the guy we were just looking at, sometimes abbreviated as SHE for standard hydrogen electrode. And they assigned it arbitrarily a value of 0 volts. So when we use this hydrogen electrode, it has an arbitrary value of 0 volts. For this reaction here, which you should recognize as an SRP sort of reaction, more so the R part, it is a reduction reaction, right? And when we look at these values, and these values are found on a table, they are all 100% reduction values, and they're all 100% reduction reactions. So when we look at this table, they will have values for the reduction reaction. So if you think about, though, the type of reactions that are actually happening here in our galvanic cell, they are redox reactions, which means they are oxidation and reduction reactions that are occurring. So the SRP value takes care of the reduction part, but we do run into a little situation here because the other reaction that you would find in the table would be incorrect in a sense, because it would not be written as an oxidation reaction. It would actually be written as a reduction reaction. So this creates a little bit of complication for some people when we go to calculate the E of a cell. And we're going to talk about it right now, and it might not make sense right at this moment, but hopefully as we start doing some examples here in this chapter, it'll make a little bit more sense for you. But first off, let's take a look at what happens, for example, if we hook up our zinc electrode with our standard hydrogen electrode. They run it on this cell, and they get a total cell voltage of 0.76 volts. You could calculate the E of the cell, or the voltage of the cell, by taking the E of the cathode minus the E of the anode in this case. So when we look at the way this cell was set up, it was set up in a way that the zinc was the anode and the hydrogen was the cathode. So knowing that the cell voltage overall was 0.76, we pretty much have this number. We know that the hydrogen electrode has a standard value of 0, which means that the cathode here would be 0. Putting those values in, we get the half reaction, or the SRP value for zinc, which is, again, you can see zinc gaining those 2 electrons, has a SRP value of 0.76 volts. Now, this equation here, when we look up these values in a table, and we'll see the table in a bit here, table of SRP values, there will be certain signs associated with the values. And what I mean by that is there will be positive or negative. And if we decide to use this equation, which is E of the cell is E of the cathode minus E of the anode, we should leave the sign alone, which means whatever you find it in that table, even though technically speaking, the reaction for the oxidation reaction is incorrect, you should leave the sign alone and not change it. And the reason for that is there is a subtraction that is happening here, which actually fixes the problem for you. So if you use this equation, and again, may not make 100% sense just yet, but if you use this equation, you should leave the signs alone in the table. You will sometimes see people say that you could calculate E of the cell by taking E of the cathode plus E of the anode. And you're like, whoa, that looks just like the same equation, except that this is a positive value here. And if you decide to use the equation where you add, which is perfectly fine, you need to actually reverse the reaction that you find in the table and actually reverse the sign. So what I mean by that is, we'll just look at the zinc one here that we just looked at. So if I go to the table, this is the reaction I'm going to see in the table. And it's going to be E naught is equal to minus 0.76 volts. Now, this is, again, a reduction reaction. This basically means that this is my cathode, right? But in our particular reaction here, the zinc is actually the anode, which means in order to make this reaction the anode, you basically would reverse it, which would put the solid zinc over here on the left, the zinc with a +2 and 2 electrons. This would be the oxidation reaction, or the anode reaction, right? And when we reverse one of these reactions, the sign changes. This becomes now positive 0.76 volts. So if we were to do our anode plus our cathode, E of our cathode plus our anode, we would need to reverse the reaction and change the sign, and that would then give us 0, which is our hydrogen cathode, plus positive 0.76 volts, gives us 0.76 volts, which is what they got for the cell in this particular case. Now, if I went to the table, I would find this number here. And if I did not want to change anything, which is perfectly fine to do as well, you could take E of the cathode minus E of the anode. Let's do the same calculation. The cathode is still hydrogen, which is 0, minus, I'm not going to change the value of my anode from the table. I'm going to leave it as minus 0.76 volts. The minus here and the minus here, turn that into a positive 0.76 volts, which again is what they got there. So I'll put it this way, and we'll do more examples, obviously, as we continue through this chapter, but you should choose one way and stick with it, because you're going to mess up if you don't. So personally, I go with the minus, and, you know, I leave the value as I find it in the table. But if you want to change it, which technically speaking, to be truthfully honest with you, this is the correct way of sort of doing it per se, because E values are specific for how the reaction is written. But if you want to change the sign, you should add. If you don't want to change the sign that you find in the table, you should subtract. So that's an important distinction between those two ways. You definitely don't want to change the sign and then subtract, because you'll undo it. So you got to choose one way and kind of stick with it. Any sort of questions on that? And again, we'll do obviously more examples and sort of demonstrate the difference between the two methods here. All right, we will lay it up there